Hi everybody, this is Professor Castanos and this is Biology 150. We're doing the Amylase activity lab this week and this is the first video which is an introduction to amylase activity. Make sure you read exercise 4B in your lab manual, especially the part where it's introducing enzymes and how they work, and specifically talks about amylase and the type of assay we'll be doing. That will be a very good introduction to this lab. Now, amylase catalyzes the hydrolysis of starch into maltose. You may remember that starch is a polysaccharide of glucose made of hundreds and hundreds of glucose units connected by glycosidic bonds. So amylase adds water to the glycosidic bonds. Specifically, every other bond of starch is broken by amylase, and this leads to the disaccharide called maltose, which is 2 units of glucose connected together. So we're going to be investigating the activity of amylase by looking at how fast this enzyme breaks down starch into maltose, and we're going to look at factors such as temperature or pH that affect the activity of this enzyme. In our lab, we have amylases from 3 different organisms, and we're going to be investigating each of these amylases and how fast they break down starch. So the first amylase is the human amylase, Homo sapiens. That's the enzyme that we have in our saliva, which starts the breakdown of starch as we are chewing our food. There's also a fungal amylase from Aspergillus oryzae in our lab, so some of you will be using that enzyme. And there's a bacterial amylase from Geobacillus stereothermophilus, which is a very interesting thermophilic bacterium. So some of you may have done a bioinformatics exercise as a homework where you looked at the sequences, the amino acid sequences of these amylases, and compared them and found out that even though their overall homology is not extensive, they do have identical amino acids at the active site, which suggests that they pretty much catalyze the same reaction in the same exact way. So we're going to be looking at what else affects enzyme activity between these 3 enzymes. And like I said, we're going to be measuring amylase activity. So enzymes function by speeding up reactions. They are catalysts, as we call them. So the way they work is that they bind specifically to their substrates, and the place where they bind their substrates is called the active site. And when they bind their substrates, they speed up the reaction between the substrates, which leads to the products. The way they work is that they typically help the reaction go faster because they bring the substrates together. They provide an ideal environment in the active site. They also may participate in the reaction more actively by transferring groups from one substrate to another. So in multiple ways, they make this reaction happen faster. So as you see here, the profile of an enzyme catalyzed reaction is much shorter than that of an enzyme of a reaction that is not catalyzed by an enzyme. And this difference in the profile here is called the difference in the activation energy. So enzymes reduce the activation energy, this little bump in the profile, by doing all of these things that we described to the substrates and speeding up the reaction. Now, since the enzymes bind the substrates to special pockets called active sites, the structure of an enzyme is critical for its function. And because enzyme structure overall, as you learned in the past, is mostly built on weak bonds, like hydrogen bonds, like hydrophobic interactions, like ionic bonds. These types of bonds are very easy to break. So things that can break any of these bonds will alter the structure of an enzyme and possibly affect its activity. So we're going to be looking at factors such as temperature or pH that may actually cause alterations in these bonds and changes in the structure, and therefore may affect the activity of our enzyme. So enzyme activity is very sensitive to environmental changes. So for instance, temperature can really alter the activity of an enzyme because, like I said, the temperature can break the hydrogen bonds or the other weak bonds between the amino acids in the 3D structure, and therefore may actually alter the shape of an enzyme and therefore change its activity. So as you see in this profile, most enzymes have similar profiles, which shows that a very narrow range of temperatures is ideal for the enzyme activity, whereas if you go away from those temperatures, the enzyme activity will be very much diminished. Especially when you're talking about higher temperatures can break those weak bonds in the 3D structure and even denature an enzyme, which would cause it to completely unfold and lose its structure and its activity. Low temperatures typically don't change the structure of an enzyme, but they lead to low activity because the enzyme is very slow to act due to lack of kinetic energy. So all the molecules at very low temperatures have low kinetic energy and therefore cannot interact, and the reaction will be slow. Now, pH is another factor that can affect enzyme activity. pH can change the chemical side chains of the amino acids, which interact in these weak interactions like ionic bonds, like hydrogen bonds, and therefore can alter again the structure of an enzyme. And so enzymes have very limited range of pH values that they like. As you see from these profiles here, these are 3 different enzymes with very different pH preferences. And so that's another very interesting factor to investigate enzyme activity. Salt can be another factor, and or any other chemicals can actually be factors that affect enzyme activity. So some of you may be investigating other factors such as salt. Now we're going to be measuring amylase activity by looking at the amount of maltose produced over time. So the faster this enzyme works, the more maltose will be produced in a certain period of time. Now maltose is not easily detectable though, so we will not be able to see maltose being produced in the test tube. It's not going to have a color or any way that it can be seen, and that's why we're doing this assay called a DNS assay. DNS stands for dinitro-salicylic acid, and it's a colored substance that can accept electrons from maltose. Maltose acts as a reducing agent. Remember, it's called a reducing sugar, and it will give electrons to DNS, and if you speed up the reaction by boiling, it's going to become reduced and change color. So reduced DNS will turn red and will absorb at 540 nanometers, will absorb light, and its amount can be measured in a spectrophotometer. So we can indirectly measure maltose this way by measuring how much DNS is produced in this second reaction, and therefore that would tell us how much maltose was produced in the first reaction. And so this is the basis of the assay that we're going to be using in this lab.